Our climate is changing, and people are looking for ways to assess the impacts, mitigate, and adapt. Climate modeling is a crucial component of researching the climate system, but climate models also provide us the projections used to do impact assessments and do climate change decision-making. But what are the climate models? How do they work? And how are the projections themselves made? I'm Dr. Adrienne Wootten. I'm a postdoctoral research associate at the South Central Climate Adaptation Science Center. For most people, climate modeling is a bit of a black box. In this video, I'll unpack the black box of climate modeling and the projections that are created from climate models, talk about the stories they provide, and some of the applications where they're used now. Let's get started. The climate projections provide us with stories of the future, which can help us plan for a changing climate. Ideally, it would be great if we only had one set of projections to work with, like this projection of temperature change in Oklahoma City. But is that really what we have? And is that really the best approach to take, to just look at one projection or one story of the future? In reality, there is more than one story from the projections. There are many stories, actually, many projections to work with. If we look again at this example for Oklahoma City, you can see there's a huge range of temperature projections, a number of stories to work with, ranging from something that's a bit cooler by the end of the century to something that's quite a bit warmer. Now, I know what you're thinking. You look at all these projections and you might have a reaction that's something like this. Don't worry though, this is what you have scientists for, like me. First question, why use more than one story? Why use more than one projection? Say you're assessing the impacts or you're planning an adaptation decision for a particular area, like say you're for Oklahoma City, for instance, and you use just this one instance in the black. Depending upon what you're really interested in, if you're using only that instance in the black, you may end up being over or under prepared for the changes in the future because you focused on that one thing in the middle rather than, okay, what's the worst case scenario or what's the best case scenario? What's the worst possible story? What's the best possible story? So planning for only one option is actually pretty risky because it ignores the possibility of a better or worse future than what you planned for. Second question, why are there so many future projections? So many stories to choose from? Let's break this down one step at a time. The first reason there are so many future projections, so many future stories to work with, is human action. Society at large has a number of possible options for what it will do with regards to energy and development. These options include things like continuing higher emissions of greenhouse gases through increased use of fossil fuels, to going with more renewable energy and sustainable development. In the climate projections, we represent this range of options for human action in terms of scenarios. In the current generation of climate projections, these scenarios are referred to as representative concentration pathways, or RCPs. In our example for Oklahoma City, then, we can go back and break things down a little bit more if we look at the temperature change based upon different RCPs. Here in this set of projections, now you only see 3, but the RCP 8.5 on the top represents a situation where we have great increase in greenhouse gases and more fossil fuel use, more fossil fuel intensive energy sources, and less sustainable development. The RCP 2.6 on the bottom, on the other hand, represents a situation where you have more sustainable growth and development in the future, more renewable energy, more other focuses on making a sustainable development situation. The RCP 4.5 is right here in the middle. It makes it a little bit easier when you break things down by the different RCPs now to see some of the range of changes and why that range of changes exists in these many different storylines in Oklahoma City. You can repeat this example for anywhere in the world. The RCPs themselves, these scenarios of human action, provide us an input to the climate models. The second reason we have so many future projections, so many future stories of a changing climate, is because of the climate models themselves. When we're talking about modeling the climate, what we're really talking about is physics, specifically many physical processes, such as the physics of the atmosphere in cloud formation, the jet stream and funnel systems, for instance, and the physics of the ocean, such as ocean currents and temperature and salinity. The global climate models, or GCMs, are mathematical representations of all these different physical processes made up of massive numbers of equations. The way they work is to divide the planet into an immense grid of boxes, both in latitude and longitude, and down into the ocean and up into the atmosphere. For any given time, it calculates all of these different equations in each of these grid boxes to give us then values of temperature and precipitation, wind speed, wind direction, relative humidity, and more for each of these locations. It does this for one timestamp, and then it moves on to the next timestamp and repeats the process over again. The GCMs themselves can be really computationally complex, and multiple modeling centers across the world actually use intense supercomputing power to run the global climate models, or GCMs, and give us their output and projections. Here's the thing. We have more than one GCM, we have many. Modeling centers across the world have created dozens of GCMs for use in the Intergovernmental Panel on Climate Change Assessment Reports and for research in general on the climate. The reason that we have so many goes back to all of those physical processes that I just mentioned that we're trying to model. All of these GCMs, though they're created in different parts of the world, and there are dozens of them now, all of them have the same fundamental physics. They all have the conservation of mass and momentum and energy, but what they don't necessarily have all the same equations for is for physical processes where we as a scientific community may not be in agreement or may still be trying to understand how that particular process works. We're of course still actively researching the climate and the atmosphere and the ocean, so having competing theories for how a particular physical process works is not unheard of. These competing theories can lead us to different equations for how to physically represent that process, and each of these equations can then be used in different climate models. Let's take a look at an example here with cloud formation. Let's say this one scientist, Smith, after years of observational study and doing lots of analysis and research on the subject, comes up with his own theory for cloud formation connected with temperature. And as a result, he creates this particular equation that relates cloud formation with temperature. This is one particular theory for cloud formation, and this is one particular equation that might be used in a global model. Let's say a couple of years later, another scientist and his or her postdocs come up with another equation after repeating analysis in a different location or using slightly different methodology to approach the same question about how clouds are formed. They come up with a slightly different relationship between temperature and cloud formation. Both of these competing theories are equally valid theories for how the clouds could be formed, and both of them could end up being represented in a global climate model. And that's where we end up with the situation of having multiple equations, multiple competing theories that can then get translated into multiple global climate models for different physical processes. Now, I just want to stress this thing with Smith and Jones here, as you might have guessed from the cartoon graphics, is entirely an example. This is not real equations. This is not real equations. This is not real equations. Disclaimer done. But this is a wonderful situation also because it's a real true example in that this kind of thing does happen with more than two theories for how something works, but also for many physical processes. So if we go back to our graphic of physical processes, many of these particular physical processes have multiple equations representing them, and as a result, they get fed into multiple different global climate models. And hence the reason we have so many different global models representing our understanding of the science, but also our competing theories for how we think the world and the climate works. And this leads us to many different stories. If we go back to our example then for Oklahoma City and we start adding different global climate models on the track with RCP 8.5, let's say RCP 8.5 was used as an input for these different global climate models, we can then end up with a situation of, oh, now we see we have more stories to work with for temperature change in Oklahoma City based upon having multiple global climate models. The fun thing, of course, is that the global climate models themselves are not often super useful actually for local and regional adaptation planning and decision making and impact assessments. And that leads us to the other reason why there are so many future stories of the changing climate, so many future projections to work with. To explain why there's another layer that goes on here and why there are so many future projections, we have to get into another example. Puerto Rico is a wonderfully complex island that transitions very quickly from the coastal landscape to the inland mountains. The positioning of the mountains and where it is in the Caribbean provides for really complex changes in temperature and precipitation as you go across the island in very short distances. Many of these dramatic changes are happen in less than 50 miles. The interesting thing, of course, when you look at it from the global climate model's perspective, is that they can't really represent that all that well. To be able to run globally, A global climate model has to divide the Earth up into a grid of boxes that is what we call relatively coarse. In a typical global climate model, or GCM, the resolution, or the size of each of those grid boxes, is 100 by 100 kilometers, or 60 by 60 miles. If you think about all those dynamic changes in Puerto Rico, you can see why this would be a problem when you're talking about climate change in Puerto Rico. All the dynamic changes just based on the landscape of Puerto Rico that affect the wonderfully dynamic ecosystems and vegetation is represented by all one or maybe two numbers in a global model compared to what you can actually see in the observed changes in temperature and precipitation over the island. Those small local features that influence temperature and precipitation don't go away in the future. So they're important as we look at local adaptation decisions and the local impact assessment for a changing climate. To translate what global climate model changes mean to a local scale, we use a process that's called downscaling. Downscaling translates the large-scale global change that happens on the continental or the global scale to what it means at a local or regional scale, bringing back all of those physical processes that are lost to a global climate model because its grid boxes are too large, or as we would say, its resolution is too coarse. Let's take a look at the United States to provide us a good example of the difference between global climate model output and the downscaled output. This is an example from global climate model output. The boxes here are about 200 kilometers by 200 kilometers. And this is actual temperature data for the continental United States and into some of the oceans. And here you can see it looks kind of pixelated, right? You can kind of make out where the Rockies are here with the decrease in temperature with elevation that you would normally expect. But the Appalachians are really kind of missing. It's a smaller mountain range compared to the Rockies. And the Rockies are much more dynamic than what you can see in the global model. There should be a lot of valleys and mountains in there where the temperature can increase and decrease dramatically over very short distances. That complexity that's there in the Rockies and the Appalachians and along coastlines, that doesn't go away in a future climate. That's still going to be there. So something like this coarse picture, is not really necessarily helpful. What downscaling does is it takes a picture that looks like this in the global models and translates it to something that looks a bit more like this. This is the downscaled global temperature. Those grid boxes in the downscaled output, or its resolution, has become smaller. The resolution has become finer. In this example, this is actually 25 kilometers by 25 kilometers. And you can actually see here a lot more detail of the changes in elevation over very short distances in the Rockies that affect the temperature. You can see the Appalachians much more clearly. And you can also see the interaction of the temperature with the coastline along the Gulf Coast and the Atlantic. Similarly to there being multiple physical processes with multiple competing theories and multiple equations that end up in multiple global climate models, there are also multiple techniques for doing downscaling. There's not one that's considered the best by the scientific community, and as a result, multiple downscaling techniques can be applied to multiple GCMs. And this gives us many more future stories, many more future projections of a changing climate. If we go back to our example with Oklahoma City, we can see this just with one scenario, one input to the global models, the RCP 8.5, we get then more lines there when we start adding in multiple downscaling techniques involved, more stories of a future climate. If we put this all together then with the multiple scenarios, the multiple global climate models, and the multiple downscaling techniques representing a range of different things from human action to scientific understanding and our ability to translate to local scale, that's why we end up with so many different future stories of a changing climate, so many future projections to work with. With so many different future stories based upon climate models and scenarios and downscaling techniques, I'm often asked then which one is the best. That's really tricky because asking which one is the best is a bit like walking into a car dealership and asking the salesperson which of these is the best. Is this hybrid the best? Is this sedan the best? Is this SUV the best? Or is this pickup truck the best? The salesperson is going to turn around and ask you, what do you need it for? What are you going to be using the car for? Are you going to be just driving around in the city, or do you need to haul stuff? There's a big difference there, and then what is the best? Likewise, I, as a climate scientist and doing climate modeling, will come back and ask you, okay, what do you need it for? What is so important to you that you're assessing the impacts of changing climate? What decision are you trying to make? And for where? For what? For why? all of that is kind of important in determining which is the best set of projections to use, which stories are most useful for your decision. What's great now is that there's numerous applications in peer-reviewed studies outside of climate science where the climate projections have been used. And these provide numerous examples of good ways to use the climate projections, particularly if there's a climate scientist involved in writing the paper. And these numerous examples come from hydrology, from agriculture, from ecology, and even from infrastructure studies. If you're intent on using the climate projections, there's a few things to keep in mind. First, one does not simply use any climate projection. Grabbing one projection or one set of data off the shelf, even though it's readily available and accessible now, is a bit like grabbing a saw and expecting it to do the same work as a hammer. If it's not meant for that particular job, if it's not the best tool for that job, it's going to end up badly for you. You can make poor analysis results for your impact assessment, or you may make a maladaptive decision. As a result, what you really need to do first is consult an expert. Before you get into using the climate projections, talk to a climate scientist like me first before you run into that particular situation where you're using data but you don't know if it's necessarily the best for what you're doing. Climate scientists like myself are here for that. We do spend a lot of time, particularly those of us in the boundary organizations like the Climate Adaptation Science Centers, here to help you make use of the climate projections for your benefit and make sure you're using them correctly so you get good analysis results and make good decisions with them. The second thing to remember when using the climate projections is that climate data can't tell you everything. The climate projections provide great future stories of the changing climate and how the climate may change in any particular region. But they can't tell you how vulnerable your species or system is. They can't tell you how risk tolerant you are as the decision maker or the person assessing the impacts. This is where the interaction between the climate scientist and you all who are using the projections for impact assessments and decision making becomes incredibly important. You're the one who knows best about what you're most concerned about. You know about your species, you know about your ecosystem, you know about everything that you're dealing with. I don't. As a climate scientist, I can't tell you that. You know that better than I do, and I wouldn't presume to tell you what you already know best. I and others as climate scientists can help you understand the projections and how the climate may change in your region. Then you can ask the situation of, okay, if this is how things change, what does it mean for what I'm most concerned about? Is it good? Is it bad? Or is it kind of neutral? Doesn't really mean anything. That happens too on occasion. But there's the wonderful thing there with this. In that interaction, you can tell the climate scientist, this is what matters most to me. I and other climate scientists are happy to help you see how the climate may change based upon those future stories. But you can also help us understand how a changing climate impacts what's most important to you. Working together, then, we can assess the impacts and adapt to a changing climate. I hope this primer on the climate projections has helped to unpack the black box of climate modeling a bit for you. If you'd like more information, you can contact me via my contact information below. I'm Dr. Adrienne Wootten. Thanks for watching.